Next speaker is Jeffrey. Jeffrey is from Stanford PhD student. He will talk about unsupervised hyperbolic learning for computer vision. So we talk now about labels. What about generation? What about self-supervision and clustering, etc. So please welcome Jeffrey.
Yeah, hello. In this third section of the talk, we will talk about unsupervised hyperbolic learning for computer vision. And the three major things we'll go over are hyperbolic generative models, so VAEs, GANs, invertible, normalizing flows, clustering, and applications mostly to image segmentation. And for this third module, we're going to focus on a few themes. So one is fully hyperbolic versus fully Euclidean layers, and then whether the operations are done in the tangent space or fully, like truly hyperbolic operations. So I guess for truly hyperbolic operations, it's much more difficult to do, like Pascal has mentioned, but operations in tangent space are it's much easier to generalize things that we already know how to do in Euclidean space. And then similarly, there's this dichotomy between fully hyperbolic layers and fully Euclidean layers, and many methods will sit somewhere in between. So we'll start with hyperbolic VAEs. So first, to create a hyperbolic VAE, we need to generalize the normal distribution to hyperbolic space. So usually for Euclidean VAEs, the prior and posterior are normal distributions, or maybe a variant, like a mixture of normal distributions. So we tried to create a hyperbolic VAE, we would also need some generalization of the normal distribution. So there are two main generalizations, one called the wrap normal distribution, introduced by Nagano et al. In ICML 2019, and this Riemannian max entropy normal distribution. And they look quite similar, but they're actually slightly different, as we'll see. So here it is. So the wrap normal distribution has a very complicated probability distribution, but it's actually very simple conceptually. So how you sample from, or maybe where it comes from, is that we would take samples from Euclidean normal distribution, and then we will map them to hyperbolic space through the exponential map. So recall that the exponential map takes Euclidean vectors and maps them into elements on hyperbolic space. And then basically that will induce a probability measure on hyperbolic space, and mathematically it's called like the push forward of the Euclidean normal distribution. And it turns out that this is easy to sample from. And the other distribution is called the Riemannian normal distribution, and this generalization, instead of like pushing forward the measure of the usual Euclidean distribution, they take the view that the correct normal distribution on hyperbolic space generalizes the property that that the Euclidean normal distribution maximizes the entropy given a set mean and variance. And there is this paper that shows that perhaps this will lead to better results. And it has a very simple form, but it turns out that it's actually much harder to reparameterize and sample from. So it requires, for example, maybe rejection sampling or something, whereas here it's the sampling for the wrap normal is very easy. So, so these papers generalize the hyperbolic VAE. So the basic idea is they take the same VAE structure and the same encoder, same decoder as Euclidean, but they now both the prior and the posterior are these hyperbolic normal distributions. And the only other difference is that we need this exponential and logarithmic map again, just to basically interface between the hyperbolic latent space and the Euclidean intermediate outputs of the encoder and decoder. So we need this exponential lap and log map. And some papers find, so this subsequent paper, Matthew et al. Finds that also that having the first layer kind of accommodate this latent geometry, this hyperbolic latent geometry, is beneficial to the performance of these hyperbolic VAEs. And the idea is to kind of generalize this Euclidean affine transformation, Euclidean linear transformation, by writing it in this following form. and then basically translating each part into hyperbolic space using the logarithmic map and other like hyperbolic computations. So you can write the Euclidean affine transformation as this sine times this norm times this distance between the input and a hyperplane, a decision hyperplane, and then you can, so a previous paper, Gani et al., actually the hyperbolic neural networks paper of 2018, did this computation and basically figured out closed form expressions for all of these quantities. And they find that, and here's a visualization of it, comparing on the left, the operation in the Poincare ball versus on the right in Euclidean space. And I guess one last thing to note is that this is somehow is not a hyperbolic to hyperbolic affine transformation. It's a Euclidean to hyperbolic affine transformation. And for hyperbolic to hyperbolic, you would need something different, and I would recommend you to check out this paper. Yeah, and here, yeah. And finally, we get the results. So as you can see, it learns some kind of interesting in Poincare space on the right. You learn some kind of interesting latent space structure where kind of similar shapes go together. So for example, we have the zeros, I guess, as the leaves of this hierarchy, and then sixes somewhere in between, and similarly for ones and sevens. And the follow-up paper that uses this max entropy Riemannian normal distribution finds something similar. And as you can see, somehow the organization in latent space, although it's completely not enforced, looks better than what it is in Euclidean space. And similarly for like the likelihoods, so at these low dimensions of 2, 5, 10, 20, there is much better, we get much better basically performance. And it turns out that using this max entropy Riemannian distribution is slightly better than using this simple wrapped normal distribution. So maybe something to consider if you're going to use these distributions. Now we talk about GANs. So here's a paper called Hyperbolic GAN, which basically generalizes the GAN in the following way. So on the generator side, there will be some number of hyperbolic layers followed by some number of linear layers, and the same thing for the discriminator. And it's, I guess, operating on this assumption that images are naturally hierarchical. So some number of hyperbolic layers may benefit the performance of this GAN. And I guess, so they find there's better sample quality. And I guess it's hard to tell from these pictures, but if we look, if we look at the FID, Frechet distance or inception score, we find that the performance is much better. And actually, in this case, there's not the qualifier, which some papers have, that the latent dimension has to be low. So I think the latent dimension is what it is normally in these GAN architectures. So if you look at the chart, what the E's mean is that E means that it's like first layer is Euclidean, then second layer is Euclidean, and then, for example, the second line, I guess you can't see my cursor, but it's basically the E and H means Euclidean or hyperbolic layer, and as it turns out, using some amount of hyperbolic layers will generally benefit the FID and inception score. And also, this works for all different types of GAN architectures. So for example, Wasserstein GAN and conditional GAN also see some benefits. And then finally, we go to normalizing flows, another type of generative model. And basically, the key idea in this paper is that we can basically map to the tangent space, apply the Euclidean flow literature that has already been developed for Euclidean normalizing flows, and then map back. So for example, let's say we have some distribution in hyperbolic space, for example, wrapped normal. Then we can map to Euclidean space using a logarithm map, and then apply a Euclidean flow, and then map back to hyperbolic space as an exponential map. And they do this typical choice where if you need an exponential map, there's actually a lot of there's a lot of different ways to apply it, because there's actually an exponential map at every point in hyperbolic space. So the typical choice is the origin, and but the idea of the second version of this normalizing flow is that actually, using the origin for both the logarithmic map and the hyperbolic map is a bit limiting. So they basically use this parallel transport to move between different points in hyperbolic space. And basically it means that we don't have to always use this origin for the exponential and hyperbolic maps. And the other key idea is that it turns out these logarithmic, exponential, and parallel transform maps are all invertible. So it turns out we can still use this change of variables equation to calculate the densities at each step. And we see some results. So it turns out, this more flexible approach of basically allowing where the exponential map and logarithmic map are applied to change works better, so both qualitatively and numerically. And also we see that performance is much better than Euclidean normalizing flows, for example, in low dimension. And then the next section, we'll talk about clustering. So hyperbolic clustering has a very close relationship, perhaps unsurprisingly, to hierarchical clustering. And hierarchical clustering is a bit discrete, but having all the embeddings in hyperbolic space allows us to, say, continuously optimize a hierarchical clustering. And that's the idea of this paper, Moneth et al. And the basic idea is to optimize a continuous version of this well-known Dasgupta's loss from hierarchical clustering. So the basic form of the Dasgupta's loss is like this. And it basically is it's like a very good hierarchical clustering loss from the hierarchical clustering literature. And then there's additional loss needed to encourage the children to have smaller norm than the parent, which basically helps the organization in hyperbolic space. So we see this is how kind of the representations are trained. And as you can see, basically it gets more and more tree-like as we apply this, this method. And we can see some applications to image embeddings. So it turns out, we can get, I guess, similar, for example, all wolves or all dogs or all instruments, we can get them into, into graph or into this tree, and naturally similar images are clustered together. And we can see the results in hierarchical clustering on a whole range of different types of data, which is not just including image data or visual data. And the last one, I guess, which is most interesting perhaps for computer vision, is this ImageNet. And we find, but it turns out the algorithm performs well over all sorts of data. And finally, we get to applications. So, for example, unsupervised image segmentation. So here we will talk about this work on unsupervised biomedical segmentation. So the idea here, I guess from the intuitive sense, is that biomedical data is inherently hierarchical. So for example, imagine you have, say, some microscopy image of a cell. There might be some natural hierarchy, say, from the cell, with the cell at its highest level, different organelles, for example, different organelles at lower levels, and then very fine structures, very fine cellular substructures at the very fine levels. And so how this approach works is that first, to adapt hyperbolic VAEs to 3D image segmentation. So for example, to replace perhaps traditional MLPs with 3D convolutional encoders. And like Pascal said, very difficult to do that in hyperbolic space. So these are Euclidean encoders and decoders. And then the idea is to first to learn discriminative representations in hyperbolic space using this idea that this image has natural hierarchy, and this natural hierarchy maybe corresponds to the segmentation labels. And then once these representations are learned, to cluster them to do some kind of unsupervised image segmentation. So we'll go through this method step by step. So I guess the first is we talked about this gyroplane layer that had been used successfully by this Matthew et al. Hyperbolic VAE paper. And we generalized this to convolutional layers in, I guess, the most straightforward way for this, for our decoder. And then to learn good representations, we use self-supervised learning. So basically, the idea is to kind of use this idea that there is a hierarchy and it exists, and then to kind of like reconstruct this hierarchy in our latent space. So the idea is that if we have a large patch, basically sub-patches of this large patch, let's call it the anchor patch, like sub-patches of this anchor patch will kind of belong in the same hierarchy. So for example, if we have a patch that contains the cell, sub-patches may contain, say, the mitochondria or other cellular substructures. And then the idea is that perhaps when we sample far away from this patch in another area of, say, a 3D volume, this belongs to a different part of the hierarchy. It's a different cellular substructure, and it belongs to a different part of the hierarchy. So they should be far away in hyperbolic space. And then what the hyperbolic hierarchical triplet loss does is to say, okay, the parent patch should kind of be higher in the hierarchy, in this case closer to the origin, and the subpatch should be within the same hierarchy, but as shown in this image, should be within the same hierarchy, but in the more lower levels, in the finer levels, closer to the leaves. And then this far away patch should be like very far away in hyperbolic space, so in a different hierarchy. And since the distance is exponential, actually like this blue point should be very far away from this I guess burgundy point and this pink point. And then so how we do it is we use a triplet loss between these sampled patches, and using this we can make sure that the related patches, which are related by, like, say, compositionally, are much closer, and this faraway patch is much more far away, and which has a correspondence that's in a much different hierarchy. And so we find that this works on, for example, on this BRATS data set, so this brain tumor segmentation data set, that it works much better than both competing work and also is also competitive with semi-supervised work. But this isn't the only one that we've investigated on. So we've investigated both on synthetic data and shown qualitative results in cryogenic electron microscopy. And then similarly, we can do discovery in the long tail with these hyperbolic representations. So it's a very similar idea that somehow the objects in the long tail are hierarchically organized. For example, so we have a couch, but or a fire or a clock, but say this couch has like basically substructures like the pillow, the blanket, etc., that may be organized hierarchically. So yeah, and we take the same approach of learning good representations and then clustering them. And so what happens is first the method uses a pre-trained mask RCNN and to get these proposals, and then applies 3 different triplet losses, which we'll go over. And basically the idea is to exploit all the hierarchy we basically get for free from this, I guess, visual knowledge of how the images work. So for example, there is a foreground background loss where somehow the foreground, which is different from the objects, which are say in the hierarchy, they should be, like the representation should be far apart. And then similarly, for example, there's this parent-child loss, which is very similar to what we saw in the previous method, where basically subpatches should sit in the same hierarchy. So for example, pillows should somehow belong to the same hierarchy as a couch. And then far away patches, for example, that might be like, in this image, like a vase or a clock or a fireplace, should sit very far in hyperbolic space, so which has the intuition that they should belong to a different hierarchy. And then, for example, the same thing with this intersecting object glass. So if we have overlapping proposals, generally they may represent different objects, so we should push them apart. And yeah, so basically various types of self-supervision help learn good features, and then we can see there's the results. So this is on Elvis, and it's a very difficult task, so all the numbers are pretty low across the board, but we do get like good, meaningful segmentations without any supervision, supervisory signals from labels. And then finally, we can get to takeaways. So for example, hyperbolic representations can outperform Euclidean representations with small amounts of data. So for example, in this unsupervised segmentation case. And then hyperbolic representations can outperform Euclidean representations at these small latent dimensions. And at larger dimensions, I guess the results are a bit more mixed. And then finally, that through these, the different methods of generalizing, for example, just using an exponential map and then doing operations in tangent space, there are simple ways to leverage hyperbolic representations. So without having to go through all the math. And then, yeah. Finally, there's the self-supervision of exploiting what we know about the hierarchy of images can be used to learn good hyperbolic representations that again can be used for downstream tasks. And yeah, so maybe we can open it up for questions.